Hi, I'm Ms Hearn. Let's get started. In this video, we're going to talk about how to draw inferences from two sets of samples. This is Chapter 9 in my statistics class, and we're going to go directly to Section 9.3, Two Means, Independent Samples. This section presents methods for using sample data from two independent samples to test hypotheses made about two population means or to construct confidence interval estimates of the difference between two population means. In Part 1 of this section, we discuss situations in which the standard deviations of the two populations are unknown and not assumed to be equal. We will not be covering Part 2 in my course. So we're looking at independent samples with sigma 1 and sigma 2, the two standard deviations, unknown and not assumed to be equal. Two samples are considered independent if the sample values selected from one population are not related to or in some way paired or matched with the sample values from the other population. Two samples are dependent if the sample values are paired. That is, each pair of sample values consists of two measurements from the same subject, such as before and after data, or if each pair of sample values consists of matched pairs, like husband and wife data. So sometimes we have to determine, do we have independent or dependent samples? In this case, it says researchers investigated the reliability of test assessment. One group consisted of 30 students who took proctored tests. A second group consisted of 32 students who took online tests without a proctor. So do you think that would be independent or dependent? The answer is that these are independent because the subjects were not matched or paired in any way. Here's another example. Independent or dependent. Students of the author collected data consisting of the heights in centimeters of husbands and the heights in centimeters of their wives. 5 of those pairs are listed below. If you guessed that these are dependent, you would be right, because the height of each husband is matched with the height of his wife. And you can imagine that the pairs might have some sort of a relationship that wouldn't exist if we randomly took the heights of men and compared them with the heights of women. Let's look at some of the notation and the formulas that you're going to use in this section. If you're looking on your formula sheet, you're going to look for the section from Chapter 9 that says Test Statistics for Two Populations. And you're going to see that we have a t-score here involving the difference of means. You're going to have a mean 1 and a mean 2, a mean 1 and a mean 2, population mean and sample means, and you're subtracting them. And we are going to be looking at the formula that involves two means independent, and we're assuming that they're not, or we're not assuming that they're equal. So that would be this section here. So we have our usual mu, sigma, n, x bar, and s representing our population mean, population standard deviation, sample size, sample mean, and sample standard deviation. But we have these subscript 1 to represent coming from the first data set, and we'd have subscripts 2 if it was coming from the second data set. The requirements are that the two population standard deviations are unknown and that no assumption is made about sigma 1 and sigma 2 being equal. The two samples must be independent, both samples must be simple random samples, and either or both of these conditions are satisfied. The two sample sizes are both large, in other words over 30, or both samples come from populations known to have normal distributions. So let's focus in on the formula that we'll be using for our test statistic. To perform a hypothesis test for two means of independent samples where sigma 1 and sigma 2 are not assumed to be equal, we are going to use this formula. You recognize it from here. You don't have to write it down or memorize it. It'll be provided, if you're in my class, it'll be provided on our formula sheet. Often it's going to be the case that the difference in the population means is assumed to be 0. That will be part of our null hypothesis. It's important to note that the test statistic is analyzing the difference in the means. That will help us to set up our null and alternative hypotheses and understand if we have a left-tailed, right-tailed, or two-tailed test. Since we're using a t-score in this case, we're going to need degrees of freedom. So what we're going to do is, since we have two sample sizes, Just to be conservative, we're going to go with one less than the smaller of the two. We're going to be using critical values. In my class, we're not going to be doing the p-value method in this section. The critical values we will find on our table A3. We will also be using all those same values to do a confidence interval estimate of mu, the difference in the means, and you can find those in the section of your formula sheet, Chapter 9, Confidence Intervals to Populations. And once again, we're looking at sigma 1 and sigma 2 unknown and not assumed to be equal. Notice here again that we're looking at the difference in the means, mu1 minus mu2. Okay, let's look at an example. So researchers conducted trials to investigate the effects of color on creativity. Subjects with a red background were asked to think of creative uses for a brick. And other subjects, so a different data group, data population, other subjects with a blue background were given the same task. Responses were given by a panel of judges. In other words, the judges gave them scores on who was more creative. Researchers made the claim that blue enhances performance on a creative task. We want to test this claim using a 0.01 significance level. So here's the data. For the red background, there were 35 data values in the sample. The mean of the data values was 3.39, so the mean of their scores on creativity level. And the sample standard deviation was 0.97. For the people in the blue background, the sample size was 36. The mean of the sample was 3.97. And the sample standard deviation was 0.63. We're comparing two data sets and we're talking about their means. We think we're going to use the methods from this section, and we need to do a requirement check. So the values of the two population standard deviations are unknown. We were not told that, and we're not assuming them to be equal. The subject groups are independent. The samples are simple random samples, and both samples sizes exceed 30, so all the requirements are satisfied. So step 1, we're going to think about our claim. The claim that blue enhances performance on a creative task can be restated as people with a blue background from group 2 have a higher mean creativity score than those in the group with a red background, group 1. This can be expressed as mu2 is greater than mu1, or in other words, mu1 is less than mu2. We always like to have mu1 to the left of mu2 in these statements, and you'll see why in a minute. So that's why we state it as mu1 is less than mu2. Step 2, if the original claim is false, then that would mean that mu1 would be greater than or equal to mu2. What we're going to do is set up our hypotheses. Our null hypothesis is always the equal to, so mu1 equal to mu2. The alternative to that is going to be mu1 less than mu2, the claim, the original claim. So that way, if we are able to reject our null hypothesis, then we would be able to accept our claim that mu1 is less than mu2. Now, the test statistics that we're going to use analyze the difference in the means. Remember, they had a mu1 minus mu2 in them. So it's helpful to think of the null hypothesis in this case if you subtract mu2 over to the left as mu1 minus mu2 being 0. That means the same thing as mu1 equaling mu2. And then the alternative hypothesis is really saying that if you subtracted mu1 minus mu2, you would get something less than 0, a negative number. So a one-tailed, left-tailed test is what we're looking at here, because we're looking at the value mu1 minus mu2 being less than 0. Remember that our significance level is alpha equals 0.01 that was given to us. Because we have two independent samples and we're testing a claim about two population means, we're going to use a t-distribution. You don't really need to memorize that because you're going to look on your formula sheet and your formula will guide you. The formula that you'll find on your formula sheet is t equals x bar 1 minus x bar 2 minus parenthesis mu1 minus mu2, all divided by the square root s1 squared over n1 plus s2 squared over n2. Here's the information that we have, and we just plug into the formula. We're going to have 3.39 minus 3.97 minus, now we're assuming mu1 minus mu2 is 0, if you recall. That was part of our null hypothesis. If we look back here, mu1 minus mu2 is 0. So that's often going to be 0. And then we're going to have the square root of 0.97 squared over 35 plus 0.63 squared over 36 equals, if you calculate it out, and I want you to practice this, you can always pause the video and practice, make sure you can get negative 2.979. So that's our test statistic, t. We have to have something to compare that to, so we need to figure out our critical values. Remember your critical values based on the significance level alpha, which was 0.01, and our degrees of freedom. We're going to use 34 degrees of freedom because there were two group sample sizes, 35 and 36. We're going to take one less than the smaller, so 34. It's a one-tailed test. Remember we talked about that because we're taking a value, mu1 minus mu2, and we're saying it's less than a number, so that's going to be to the left. A left-tailed, one-tailed test. So the area in one tail is going to be the entire alpha, the significance level 0.01, and we're looking at 34, so the critical value is going to be 2.441 plus or minus. All right, it's a left-tailed test, so when we draw our picture, we're going to use the left side value, negative 2.441, and we're comparing that to our test statistic that we calculated on the previous slide, which turned out to be negative 2.979. Since that's to the left of negative 2.441, that is in our rejection region. Because the test statistic does fall in the critical region, we reject the null hypothesis that mu1 is equal to mu2, and we accept the alternative hypothesis that mu1 is less than mu2. So therefore, there is sufficient evidence to support the claim that people with a blue background, which was group 2, have a higher mean creativity score than those in the group with a red background, group 1. We rejected our null hypothesis, and therefore we're going to accept our claim. I hope you found this video helpful. If you did, please remember to like it because that will help other students to find the video.